I mean, we don't have to do it in person, right? Like, it's up to me. I decide this. So, like, I have to know how bad people are doing, and if they're doing really bad, then we can make it online. But I mean, you'd already dropped out, so I don't know why I'm looking at you. But you wanted A plus? I don't know. I mean, I don't know what to say. All right. One. All right. Can you hear me? Hello? Can you hear me? All right, good. All right. Let's go. All right. Good. So last time we talked about you could have a constraint problem, and as you might remember, these are very hard to work with. For one thing, you need to find feasibility, right? So you have to find where h of x is 0. So numerically, this is very ugly. So people have done the following. They said, okay, forget about it. Just add a penalty term and allow x to be any real number. Okay? So you went from a constraint problem to unconstrained. Okay? And and then you take c to infinity to get back the constraint. So last time we did this example. Oops. So we had this constraint problem. I found you the Lagrangian. I minimized it using stationarity. And I found my minimizer, x. And then we observed that as you take c to infinity, you get back your minimizer. All right? So again, this method is called the penalty method, and you're going from a constrained problem to an unconstrained. Okay? All right, so good. And we use this to do numerics, meaning I'm doing numerics for the augmented Lagrangian. Okay, oops. All right. Good. So we have the following formula. The minimizer of the unconstrained problem is about equal to the constraint problem. Okay. All right. So now I have to prove this statement. So here's the statement. Suppose that you have a minimizer, x star lambda star. Then your augmented Lagrangian will have the same minimizer. Okay. So I'm going to prove you this. So in other words, I'm making rigorous the following statement. Let me write it again. Minimum of LC is about a minimum of F, given that H of X is 0. Huh? Oh, because you have to take limits. This is as you take C to infinity. So you have the same minimum, but not the same value, because this guy still has a C there. Yeah. So you have to take a limit. Well, okay, I mean, let me say it this way. Fine, let me do it this way. If you put lambda star, then yes, they're equal. Okay? But if you wanna, anyways, this is what we're doing, yes. Let me just say that. All right? This is what we're proving. All right, so here's what you need. Let me return. So you have the Hessian of the augmented matrix, and so this is the Hessian, right? So I simply take twice nabla of this whole expression. So let me do this with you. So the double nabla of C over 2 h of x squared. Oops. Like this. Is what? Well, you do it once and you get C over 2 times 2 h of x gradient of h. Okay. And then you do it again and you use product rule. So you have h of x with transpose plus whatever I wrote here. So h of x Hessian of h. Okay? All right, good. Then we call them as follows. I call the first guy A and the second guy B. Let me ask you a cool question. Suppose you know that your matrix B is of the form V transpose V. Can someone tell me why this matrix is positive definite? Any guesses? So let's do it together. So we have x b x. So this is oh wow, yeah, you can do it that way as well. That's right. Yeah, that's right. So you have no. The way I wrote it is, you might be right. Let me check. So how do I want it? So I wanna go click. Yeah. So I don't know. Depends on what you think of V. It's not the dot product. So let me do it with you. V1 Vn V1 Vn, and you have the following matrix. So you go V1 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 V2 V1 Vn V2 V1 V2 Vn, and then Vn, right? But anyways, I mean, you can't really see it from here. It's a mess. The point is, you have this guy, and this guy, and then you write it like this. So, and you get something like this. Okay? All right. So, fine. What does arg mean? Oh, that was an old. Let me find it. And I'll just tell you here. Yeah, arg mean means the following. So when someone says arg min of a function, given that x, let's say, is positive, they're asking you for x star. Okay. So f of x star is equal to the min of f of x, x in omega, whatever. Is that okay, Daniel? Okay, good. All right, so this guy is positive definite, and A is positive definite on the set where the gradient of h times v is 0. Do you know why? Which condition we're using? Do you remember? So this is the KKT. So this is one of the KKT conditions, that the Hessian of L is positive definite on the tangent space of all the V who are normal to the constraint. Okay, that's all. So you have these conditions, and so you go back to the lemma we proved last time. So let me just go to the statement. Yeah, well, so yeah, we proved that if A is positive on bx0 and this guy always, fine, okay, whatever. Then A plus CB is strictly positive when C is large enough. All right, all right. Okay, so yeah, by KKT, this matrix is positive definite on the tangent space. This guy is also positive definite. So we are in the setting of the previous lemma, and we get that this Hessian is positive definite for large enough C. And so that means that X star, lambda star are minimizers by KKT. So by KKT, X star, lambda star minimize LC, the augmented Lagrangian. Okay, so I mean, okay, if it confuses you, put C equals 0. Okay, then we just have the Lagrangian, and this is the Lagrange multipliers theorem. All right, so think about it this way. What happens when the Lagrange multiplier theorem, you add another penalty term? And it says, it's okay. As long as it's big enough, you still have the theorem. That's all. Okay, now that you have this, we can finally talk about the method. So, augmented Lagrangian. The technique here is you want to find the minimizer of f by minimizing the augmented Lagrangian. Okay, that's what the theorem tells us that we just proved. That if you want to find x star lambda star, you can find the one for the augmented. And why would you do that? Why would you go from a simple expression to a complicated one? So let me ask you, why will I go from minimizing this for h of x equals 0 to the whole guy here? What was the benefit? Do you remember? Just to see if you follow. Why did we introduce the augmented Lagrangian? Yeah, that's all. So now this is an unconstrained problem, and you just used second year calculus. So you set it to 0. Okay, so you set it to 0. And now let me give you the steps. So here you have to move back and forth between your multiplier and your x. So this is a two-step algorithm. We will have an update on lambda k plus 1, and we're going to have an update on the space show position, okay? So we need both. All right, you have to start from somewhere. So we start with this multiplier, and now let's find x1. So if you remember from the Lagrange multiplier theorem, you fix your lambda, and then you want to minimize the Lagrangian, okay? So you minimize it, that's what we mean by argument. And yeah, whatever. So you want to minimize this expression, so you use the first order condition. So I take the gradient of this and set it to 0. All right, so that's what happened here. So I took its gradient, and I have gradient of f, gradient of h, and then by a chain rule, I get this expression. What else? Yeah, anyway, so this is a typo. This would be plus over here. So let me write it. So this is a parenthesis lambda 0 plus ch of x1. So yeah, anyway, so I moved this to the right. All right, good. What else? Yeah, so now you have one expression for the gradient, and I'm going to get you one more, and that will give me the algorithm. So you want your lambda 1. So again, remember, I have lambda 0. I just found x1. Now I need to use this to find lambda 1. And then I'm going to use lambda 1 to get x2. And I'm going to use x2 to get lambda 2. And so on. Okay? So I found x1 by minimizing this expression. Now I'm going to find lambda 1. Well, I want my lambda 1 to satisfy the usual Lagrangian, right? So the Lagrangian is this guy, f of x plus lambda h. Okay, so I want this to be satisfied. So then I get this expression. Okay, that's all. Now you equate the two. So on one hand, you have your Lagrange multiplier theorem, and on the other hand, you have the penalty approach. And then you solve for lambda 1, lambda 0. So the h's cancel out, and you're left with this. Okay? Sorry? So this is up to you. In the textbook, they usually have it to be a sequence as well. But you can also have it just be c, the constant. And you can take c to infinity. Okay? So some really big number. But yeah, I mean, yes. Right, so here's the general algorithm. Yeah, so C can be some sequence alpha K. For example, take C to the K where C is bigger than 1. Okay, like an exponential sequence. And yeah, so start with lambda K, minimize your Lagrangian, and get the next multiplier through this recursion. Okay. So again, let me see what happened. We went to the unconstrained problem because we don't want to deal with the feasibility issues. It's hard to do numerics over that. So we added a penalty term. Then we said, okay, set this guy to 0. Set this guy to 0 and solve it to get x1. Okay, so you start with the multiplier, you get your minimizer x1, and then you find your next lambda by using the stationarity of your original function. Okay, and that's the algorithm. So I think the example is next. Okay, good. So yeah, let's do an example to give you the idea of what's happening. Same problem as before. And we already know the minimizers because why? If you just put 1, you get min of 1 plus y squared over 2 over all y, right? In this case, the smallest when y is 0. So that's why you get 1, 0. Okay? It's a stupid problem, but it gives you the main idea of the method. So again, I need to make my problem unconstrained because it's much easier to work with. So I have to pay for it with a penalty. You set it to 0. And when you set it to 0, you find a relation of xk plus 1 with the previous step. Okay, so if you like, let me do it slowly. Pick lambda 0 to be 1. Take all the ak's to be constants, c. Okay, and then you just got that x of 1 is equal to c minus 1, c plus 1. Okay, that's all. Now that you got your x, you want to find your next multiplier. So you just compute h of the minimizer. And what is h? H of x is equal to x minus 1. Okay, so then I just plug it in. I solve for, okay, I'll solve it because it got lost. So I go from, so what it says there is lambda k plus 1 minus minus 1 over lambda k minus minus 1 is equal to 1 over 1 plus ak. And this is what we called the rate of convergence. Okay. And why is it called the rate? Because call this guy R, RK over, I'll do it by hand. So you have lambda k plus 1 minus minus 1, if you like lambda star, and you get 1 plus ak, lambda k minus lambda star, and you keep solving it till you have all of them. Okay. And if you take them all to be the constant c, this guy became 1 plus c to some constant k. So it goes to 0. Okay. So what just happened? My multiplier, lambda, converged to -1, which is the same one I found from the minimization. So how do I get this lambda? I have x squared y squared over 2 plus lambda x minus 1. You set this guy to 0, and you use your constraint. The first guy gives you, we talked about this last time. It was x plus lambda, right? And then x equal 1. And this gives you a lambda equal -1, x equal 1. All right, anyhow. So what just happened? So this is a very trivial problem if you use Lagrange multipliers. But I don't know, suppose this is like some massive problem with many lambdas. We just build a sequence for you that converges to the lambda star from Lagrange multipliers. Okay? All right, good. So again, this algorithm moves in two ways. It approximates the minimizer, and it also gives you the Lagrange multiplier. It gives you both. Okay? So it solves both the primal and the dual problem, because this guy is called the maximizer of phi lambda. Okay? All right. So this is a point of view from the book, the one I explained to you, the augmented Lagrangian. So you start again with the augmented Lagrangian, and you do a change of variables. So you call x of x, h of x to be y. So you have y. And then you use the primal function, which, let me remind you, omega y is equal to the minimum over x of f of x, given that h of x is y. Okay? So again, this is an unconstrained, this is unconstrained. All right? This is an unconstrained problem. So why did they do that? Because if you remember, we have a picture for the primal function. So let's see the picture. Yeah, suppose x carries the minimizer from the, the algorithm, right? So again, let me write the algorithm so that you don't forget. Start with lambda 0, and then get x1 by minimizing this guy, f of y lambda 0. Okay? And then 3, get lambda 1 from lambda 0 plus c of h of x1. Okay? That's the algorithm. So you get your x of k from minimizing this guy. Or okay, yk, whatever. And yeah, so since it's a minimizer, it satisfies first order condition. And what did I do? So I have gradient of omega plus lambda of this, which is just 1. And then I have c y equal to 0, right? Okay, good. But then here you use your algorithm. This is the ALM step. Okay. So what just happened? Fine, okay, let me say that as well. So yk plus 1 Went. I forgot. How did I get this? The next can be found from solving this. Why? Oh, wait. Yes. Yeah. So what we did here is we solved the equation gradient of Fy at yk plus 1 at lambda k plus 1 equal to 0. Okay? So this is a little bit nicer because you always solve the same equation. Okay, so let me describe. This is the same algorithm, but using the primal function. All right, so let me explain what happened. Again, you start with lambda 0. You get, let me do it from here. You get y1 as the argmin of Fy lambda 0. And then, good. And then I get lambda k plus 1 from solving f of y1 lambda k plus 1. Okay? So let me say what happened. So start with lambda 0, get this, and then from here get lambda 1. Okay, I'm going to do an example. This is too theoretical. So, but I mean, you get to choose what to do. You will have some question like of just writing the first few steps, and it's up to you. Either you go with this, where you simply set it to 0 each time. You'll see in the example, or you go with the other one we talked about. All right. So why this is cool? So again, this is from your book. Let me zoom in. So it describes ALM. So I should start from lambda k. Okay, so let's pretend that lambda k is lambda 0. This graph, yeah, as you can see, it's the primal function. Okay, so it's the primal function, and then you set, oh, no, I mean lambda 0. And yeah, so you find the location on omega whose gradient is equal to omega y. So you start with this and you solve for y. So you find some y. You call it y1. And they call it here yk. All right, so they have this slope, okay, and they find y1. Then to find the second guy, you solve this system again. So you have lambda 1 is equal to minus gradient of omega y1. You solve it in reverse, right? You solve it in reverse, and that gives you the slope, lambda 1. And then you continue. So then again, you find, where are we? Oh, I have to change a little bit. So this should be plus cy squared over 2. And this is like this, yeah. But yeah, and then, right, so then to find y2, so step 3, to find y2, you solve the minus gradient you solve the following. Lambda 1 equal to minus gradient of omega y plus cy squared over 2. So this is how ALM works. Each time you pick a slope, then you have to pick the minimizer approximation, and the minimizer approximation gives you the next multiplier, and then the next slope gives you the next step, so on. All right, let's do an example to see how this works. Yeah, see, but yeah, you can change it. It's not a problem. Yeah, you can have it be AK. Yeah. All right, let's do this. So this is your function, and I need the primal function. So how do you solve primal function? You call h of x to be x minus 1. And instead of setting it to 0, you set it to u. Okay, this is the primal function by definition. But then this is a stupid problem because all I have to do is plug in 1 plus u and then minimize over y. But again, the minimizer is at y equals 0. Okay? All right, good. So this is your primal function. It's very nice. Let me draw it for you. So this guy is, where is it 0? When u is 0, what happens? You get a half. So you have, it's like this. Okay? Okay. So this is where, the function we're going to play our ALM game. All right. Huh? What happened? What? Oh, did I make a mistake? When u is 0, you get a half, right? Oh, you're saying it's flipped? Oh, yeah. That's right. So, okay, what's my mistake? That's right. So it just says that it hits at a half. Thank you. Yes. Good. Good. Thank you. All right. So let's do our algorithm. You start with some lambda 0. I don't care. It doesn't matter because it will converge regardless. Say lambda 0 is 1. So not minus 1, the total opposite, to see how fast it goes. Then to get your lambdas, to get your u1, your first iteration, we solve the augmented Lagrangian, right? And when we did that, we said it's the same as the first order condition with the primal function, okay? So then I just take u derivative. So what's the u derivative of 1 plus u squared? It's what? Yeah, it's 1 plus u. So we have 1 plus u here. And I solve for u, and I get my first spatial step, okay? So I started with the multiplier, and I got my first spatial step. All right. Now I need to find my next multiplier. Right. So, yeah, anyhow. So again, the way we find the multiplier, we so what was the logic? I forgot. Right, I set the gradient. Okay, whatever. So yeah, the next multiplier, you have to take the gradient of your primal function. So I want to draw this picture. It's too confusing like this. So you have this guy, which is basically a line, right? So this is the line 1 plus c plus 1 u equal to, I don't know, gu. So when does it, when u is 0, you get 1, and c plus 1 is big. So, and when this is 0, so it goes like this, right? Okay. So this is the line 1 plus c plus 1 u. And then this guy, it was just 1 plus u equal to g prime u, or I mean g tilde, whatever. And this guy hits has the same intercept, but then it hits it at -1, right? Okay, let me draw this bigger because it's nice. So this guy goes like this. This is the 1 plus u. And the other guy was 1 plus cu equal your function. If this is 0, so it goes like this, different color. All right. So the blue guy is 1 c plus 1 u. And this intercept is -1 plus c. Okay? All right, anyhow, the point is how this algorithm works. So, yeah, this is the gradient of omega. So this is the gradient of omega. And this is the gradient of omega, but then you also have your penalty. Okay? And the way we did it was, let me do the first step. Lambda 0. Whatever. So yeah, anyways, to find lambda 1, first I need to find y0, and then, so pretend lambda 0 is 1. Oof. And then y0 is what? It's 0. No, it's -2, 1 plus c. So this is y0. Okay. All right. And then you want to find lambda 1. So you go upstairs over here. Okay. And the slope of this guy will be lambda 1. Okay. I know it's confusing, but like that's how the algorithm works. So it went from here. We found the blue guy. He gave us y0, and then we went up here, and he gave us lambda 1, and then you will have to go up there and. Anyways. But you don't have to do this. I just want you to be able to do the numerics. So I solved this equation, and I got my y0, and then I plug in my y0 in the gradient, which was -1 plus u. So I plug in this guy and I get this. And then I isolate for my minimizer. So from before, you already know that the minimizer is lambda star -1. Okay, that could be like a part A. And then the next part would be find the sequence that goes to it, then give the rate. So the rate is 1 plus C. So, yeah. Okay, so I don't know. Is that okay? If you have a question, just let me know. I don't know. So that's how you. So it's up to you. Either you do it the primal function, or you do it. I do it both ways for you, and you pick the one you like. Doesn't matter. So I also did it by hand. Okay. So either you find it like this, or you do it with the primal function. Either way. All right. Um, yeah. What do I want to say? Yeah, we talked about this. So, so if you look at a slightly different function, FC lambda, so this is almost like the dual, but you also have the penalty. So I don't know if you remember, but last time we computed the gradient of this dual, and we found it to be the constraint. So there's an accidental beautiful thing happened here, that ALM is the same as steepest descent, ascent, I'm sorry, for the dual. Okay? Which is, I mean, I don't know, you probably saw it by now. Like all this time I'm computing lambdas, and all these lambdas converge to a lambda star, which you know that phi lambda star is equal to the maximum of phi lambda, the dual. Okay? So if you don't want to think ALM because it's a bit complicated, think that all we're doing is we're doing steepest ascent for the dual problem. That's all. Whatever you like. Okay? So both point of views work. They're the one and the same. All right. So what else? Anyways, I mean, it's fine. Thank you. Yeah, sure. Yeah. Oh, because like, I mean, numerics is not really like, yeah, it's for systems that you cannot solve it. Like, it could be like 1,000 by 1,000 vector. Like, I mean, yeah, like a huge vector, 1,000 entries.
Also just like take
No, but, yeah, that's right. Yeah, each time, that's right, each time, yeah, this is some out of date. And each time you have to minimize, or there's a, I'm supposed to have a minimum. Yeah, so each time you have to minimize. For each alpha thing, yeah. But the beautiful thing is it's an unconstrained problem. So there's no, you don't have to look at tangent spaces, you don't have to, there are no constraints, just compute the gradient.
So why do you have a meaningful response?
Oh, yeah, I have that, yeah. I'll do that on Tuesday. But it's not hard, let me just tell you. So when you have this thing, you want the slack variable. Yes, that's exactly, yeah. Yeah, like the simplex method, I was talking to you last time, but you were basically you remember that picture from the duo. Yeah, whatever. Even this case, cool. Yeah. So in simplex method, what did you do? You had some formulas, and then you had a hyperplane, and the first thing it touched was the minimizer. So you had to pick some slope. I mean, simplex method, of course, you can work with the table, but there's a point of view where you put the pivot, and the pivot is the angle. And you now want to put the pivot in this like slope from the start. And again, you have a sequence of numbers, and you try to approximate the vertex at start. So, because you cannot take derivatives in. Maybe I should. Okay, here's how there was a homework. Yeah, there was a homework in your textbook that it showed that the quantitative gradient method is the same as Gaussian elimination. And with Gaussian elimination was a simplest method. And you just put the rows around and solve it. Remember? Okay, I mean that's what you do. I mean what like I don't know, but I will have to do like a matrix example. And then trying to find out, I will have to see how the slope is taken. Because you had some inverse matrix, right?